Welcome to the Sleepy Astronomer. I'm thrilled you've drifted in tonight to join us under the starry canopy. Before we dive into why stars twinkle, I'd love to know, where in the world are you watching from? Drop your location in the comments and let's explore the night sky together. When we gaze up at the night sky and see stars gently blinking, shimmering, or seeming to dance, we're witnessing something both magical and deeply rooted in physics. This flickering, often described as twinkling, is not just a poetic illusion, it's a real, observable effect that has puzzled and fascinated humans for millennia. Long before modern science explained the phenomenon, ancient storytellers and poets attributed star twinkling to the laughter of the heavens, or to celestial spirits playing games in the vastness above. But what is this twinkling really? What are we truly seeing when a star appears to pulse or shift in brightness and colour? Twinkling, in scientific terms, refers to the rapid variation in the apparent brightness or position of a distant star when viewed from Earth. This variation can happen so quickly that the star appears to shimmer, blink, or even change hues for a split second. It's almost as if the star is breathing, alive in the vast silence of space. But of course, the star itself isn't changing. Its light is being affected on its way to us. The light we see from stars has been travelling for years, sometimes even thousands or millions of years, across the vast emptiness of space, undisturbed and unchanged. For the most part, the vacuum of space is a quiet, steady environment for photons to travel through. But the final leg of their journey, the last few hundred kilometers as they enter Earth's atmosphere, is anything but steady. It is here, in this thin veil of moving air and constantly shifting temperature, that the light is disturbed, scattered, and bent. Imagine holding a coin at the bottom of a swimming pool. When you look at it from above, the coin seems to shift slightly depending on how the water is moving. Tiny waves and ripples in the water surface distort your view, making the coin appear to flicker or shimmer. That's very similar to how star twinkling works, except the ripples are in our atmosphere and the coin is a pinpoint of light from an unimaginably distant star. You might also think of the star as a tiny flashlight pointed directly at you from the other side of the universe. This light travels in a straight line until it hits our atmosphere. Then, as it passes through layers of air with different temperatures and densities, it bends and scatters slightly. These changes happen rapidly and randomly, so the direction the light is coming from seems to wobble. To your eyes, it looks like the star is dancing ever so slightly, flickering from one tiny spot to another. Your brain interprets these shifts as changes in brightness and position, and thus you perceive the star as twinkling. But what makes stars unique in this way is how compact their light appears to us. Even the largest stars in the sky are so far away that their light reaches us as if from a single point. This means any small atmospheric distortion affects the entire image of the star. Planets, by contrast, appear larger, still tiny, but with a small disk of light rather than a pinpoint. This small but extended size allows the distortions in the atmosphere to average out across their surface, which is why planets don't usually twinkle the way stars do. So twinkling is a beautiful combination of cosmic distance, the purity of starlight, and the restless breath of our own atmosphere. It's a nightly dance created not by the stars themselves, but by the invisible currents of air that surround our world, currents we can't see, but that leave their signature every time we look up at the sky. And while it may seem like just a quaint feature of the night sky, twinkling actually tells us a lot about the conditions of our atmosphere. The degree to which stars twinkle varies depending on temperature gradients, air turbulence, and the overall stability of the air above us. In this way, that subtle shimmer of starlight is not only beautiful, it's informative. It's the sky whispering to us, telling us about the winds and waves of the unseen air above. So next time you see a star wink at you in the dark, remember, it's not the star changing, it's the earth breathing. One of the most curious things about the night sky is that not all the celestial objects we see behave the same way. On a clear evening, as you lie back and gaze upward, you might notice that while most stars seem to flicker and shimmer, a few of the brighter stars remain steady and calm. These steadier lights are often planets, Venus, Jupiter, Mars, and Saturn among them. They might shine just as brightly, or even brighter than the surrounding stars, but they don't twinkle the same way. Why? The answer lies in a fascinating difference between what astronomers call point sources and extended sources of light. A point source is an object that is so far away and so small in apparent size that it appears as a single point of light to the naked eye. Stars, being light years away from Earth, fall into this category. Even though some of them are much larger than our Sun, their immense distance makes them appear as infinitesimally small dots of light in our sky. Planets, on the other hand, are part of our solar system. Though they are still millions of kilometers away, they are significantly closer than stars, close enough that they appear to have a small disk when viewed through a telescope. To the naked eye, this small size is imperceptible as a disk, but it's just large enough to make a crucial difference. Because planets are not true point sources, they don't twinkle in the same way. Their light is spread out over a slightly wider area, and this makes them more stable in appearance. Here's how this works in practice. As starlight enters Earth's atmosphere, it passes through layers of air with varying temperatures and densities. These layers act like moving lenses, constantly bending the light in different directions. Because stars are point sources, these tiny shifts affect all of their light at once. So when the atmosphere bends the starlight one way, the whole image of the star moves slightly, and your eye sees it flicker. This happens many times per second, causing that familiar twinkle. Now imagine the same thing happening with light from a planet. Because planets appear as small disks rather than tiny points, different parts of their light may be affected differently by the atmosphere. One part of the disk might be bent slightly upward, while another part is bent slightly downward, and yet another may remain unaffected. The result is that these atmospheric distortions tend to cancel each other out when they reach your eyes. Instead of a single concentrated beam being knocked around, you get a collection of beams that even out. The planet, therefore, appears to shine more steadily. You can think of it like trying to watch a candle flame through a turbulent window. If you look at a single small candle far away through the heat rising off a hot surface, it wavers and shifts. But if you look at a wider light source, say a lantern with a large flame, the flickering gets smoothed out. This analogy helps us visualize why a planet, though not truly large to our eyes, is large enough to resist the flicker. The difference in behavior is so noticeable that it actually helps skywatchers identify whether a bright object is a star or a planet. If it twinkles rapidly, chances are it's a star. If it shines steadily, especially if it has a slightly yellow or reddish hue and doesn't move much from night to night, it's probably a planet. Amateur astronomers and stargazers have used this trick for centuries to tell the difference without any equipment at all. It's also interesting to note that planets can occasionally twinkle, especially when they are low on the horizon. In these cases, their light is passing through a much thicker slice of the atmosphere, just like stars in the same position, and this increases the likelihood of noticeable distortion. However, even in these cases, the twinkling is usually far less intense than that of nearby stars. This distinction between point and extended sources is not just useful for casual observation. It's also critically important in astronomy. When building telescopes, for example, engineers must consider how different light sources will behave when they pass through Earth's atmosphere. Telescopes located at high altitudes or even launched into space, like the Hubble Space Telescope, are designed to eliminate or avoid the distortions that cause twinkling, allowing scientists to study stars with incredible clarity. But even the best telescopes on Earth can't completely eliminate the difference between a pinpoint star and a broad planetary disk when dealing with atmospheric turbulence. So next time you gaze at a bright, unmoving light in the night sky and wonder whether it's a planet or a star, remember this simple but profound truth. The way it twinkles, or doesn't, tells a story. It's not just light, but geometry, distance, and physics all playing together in a silent symphony. Stars twinkle because they are far and focused, tiny points of light piercing the veil of our atmosphere. Planets shine more steadily because their light, though still distant, is broad enough to resist the winds and waves of Earth's upper air. The heavens, it turns out, are not just beautiful, they are precise, and every shimmer tells us something real. As soon as starlight enters Earth's atmosphere, it begins the final, and most turbulent, stage of its long journey across the universe. This thin, invisible shell of gases that surrounds our planet is far from empty or still. It is a constantly moving, breathing, living system made up of swirling currents of air, pockets of varying temperature, fluctuating humidity, and layered densities that stretch upward for hundreds of kilometers. To understand why stars twinkle, one must understand this atmospheric dance, for it is here, within Earth's ever-shifting veil, that the once stable light from distant stars becomes disturbed. Think of the atmosphere as a dynamic lens, but not one made of smooth glass. Rather, it's a lens in motion, a sea of invisible rivers and whirlpools of air flowing at different speeds and temperatures. It is layered, with each layer behaving differently depending on altitude, local weather conditions, the time of day, and even the season. As starlight travels downward through this chaotic system, it passes from one layer to another, and each transition bends the light ever so slightly, a process known as refraction. Refraction occurs because light travels at different speeds through materials of different densities. When starlight passes from the vacuum of space into the denser gases of our atmosphere, it slows down and bends. This bending becomes unpredictable when the atmosphere itself is unstable. As the light continues through countless layers of moving air, each with its own temperature and pressure, the direction of the beam shifts ever so slightly over and over again. It's not unlike a marble rolling over an uneven floor. Each bump or groove causes a tiny deviation in its path. The primary culprit behind this instability is temperature. Warm air is less dense than cool air, and the atmosphere is filled with constantly shifting patches of both. These differing temperatures create variations in air pressure and density, which bend and scatter the incoming starlight in different directions. The boundaries between warm and cool pockets of air act like miniature lenses, each distorting the light in subtle and constantly changing ways. Imagine that the star is trying to send you a message, a perfect, unwavering beam of light. But between that star and your eye is a funhouse mirror made of air. The mirror is wobbling, stretching, shrinking, and swirling. Sometimes it speeds up the light, sometimes it slows it down. Sometimes it bends it one way, then bends it back. And it does all this randomly, many times per second. By the time the light reaches your eye, it has been jostled and redirected so much that the star no longer appears as a calm, steady point. Instead, it appears to shimmer, flicker, or even slightly change colour. That's twinkling. This turbulent nature of the atmosphere is more than just a nuisance for stargazers. It's a well-known challenge for professional astronomers. In fact, there's a specific term for the way atmospheric conditions affect the clarity of astronomical images: seeing. Good seeing conditions mean the atmosphere is relatively stable, with fewer pockets of turbulent air. Under these circumstances, stars appear to twinkle less, and telescopic images are clearer. Bad seeing conditions, such as those caused by high winds, warm ground surfaces radiating heat, or unstable weather systems, make stars twinkle more, often dramatically so, and blur the images astronomers see through their instruments. That's why observatories are often built on mountaintops or in deserts. These locations tend to have more stable air, less light pollution, and drier conditions. At higher altitudes, the observatory sits above much of the lower, denser, and more turbulent part of the atmosphere. The less atmosphere starlight has to pass through, the less it is disturbed, and the less twinkling occurs. Another fascinating aspect of our dynamic atmosphere is how it can cause stars near the horizon to twinkle much more than those overhead. When a star is directly above you, its light takes a relatively straight, short path through the atmosphere. But when the star is near the horizon, its light must pass through a much longer stretch of air. Not only is this path longer, but it passes through more layers of atmospheric instability, increasing the amount of distortion. That's why stars near the horizon often appear to flicker violently, changing colours rapidly and seeming almost to flutter like candle flames. The ever-changing state of the atmosphere also affects the colour of starlight. Since different wavelengths of light bend by different amounts, a process known as dispersion, the bending of light can separate its colours slightly. That's why, during intense twinkling, you may see flashes of red, blue or green coming from a single star. The atmosphere is literally prying the colours apart and sending them in slightly different directions. This shimmering rainbow effect adds to the wonder of stargazing, but is yet another sign of the atmosphere's restless nature. Ultimately, Earth's atmosphere is both a gift and a challenge. It protects life, regulates temperature, and gives us breathable air, but it also blurs the universe for those who look upward. The same layers that bring us weather, clouds and sunsets are the very ones that make starlight dance. It's humbling to think that the flicker of a star is not caused by the star itself, but by the air just above our heads. And yet, this natural interference adds something uniquely poetic to the experience of looking at the night sky. Twinkling is not a flaw to be corrected. It's a reminder that we observe the cosmos not from a perfect vantage point, but from a living, breathing world. The stars twinkle because our planet is alive. Every flicker is a testament to Earth's shifting skies. A gentle, beautiful distortion that connects our little world to the vast and steady light of the stars. To truly understand why stars twinkle, we must look more closely at the behaviour of the air that surrounds us. Specifically, how differences in air density and temperature play a vital role in bending the light that travels through it. The atmosphere may seem like an invisible and uniform layer, but it is, in reality, an ever-changing ocean of gases layered upon itself, filled with variations in heat, moisture, and motion. These differences are not subtle, they are profound, and they shape how starlight reaches our eyes in ways that we can both see and feel. At the heart of this twinkling effect is a simple truth of physics. Air of different temperatures has different densities. Warm air rises because it is less dense than cool air. Cold air, being heavier, tends to sink and settle in lower areas. But the atmosphere is not neatly organised like a layered cake. It is a swirling, boiling stew of air masses constantly in motion. As sunlight heats the Earth's surface during the day, that warmth is transferred to the air just above it, creating currents of rising warm air. At the same time, cooler air from higher altitudes flows downward. This churning creates an ever-changing patchwork of air cells with different temperatures, and therefore different densities. When light from a star enters Earth's atmosphere, it travels in a straight line until it encounters these pockets of differing air density. Each change in density causes the light to bend slightly, a process known as refraction. These bends aren't uniform or predictable. They happen randomly and rapidly as the light passes through one turbulent layer after another. One moment, the air may be slightly cooler and denser, bending the light more. The next, a warmer, lighter layer might let the beam pass through with less deviation. This constant bending of light, caused by changes in density driven by temperature fluctuations, is what causes a star to appear to twinkle. You might think of this process as being similar to looking at something underwater. If you've ever opened your eyes in a swimming pool or looked at an object submerged just beneath the surface, you may have noticed how distorted it can appear. This happens because light travels differently through water than it does through air. If the water is perfectly still, the image is only slightly distorted. But as soon as the water begins to ripple, the image shimmers, shifts, and bends, sometimes appearing in one place, then another. Now imagine looking at that object through not one layer of water, but through dozens or even hundreds of constantly rippling layers. That's what starlight endures as it travels through Earth's turbulent atmosphere. But the situation is even more complex. Temperature changes don't just exist between high and low altitudes. They can happen horizontally too. Wind can carry a mass of warm air over a cooler region, creating a sharp boundary, what meteorologists call a thermal gradient. These gradients are particularly potent at night, especially after sunset, when the Earth's surface begins to cool quickly. That cooling can create sharp contrasts between the ground level air and the warmer layers just above, further stirring up the atmosphere and creating pockets of turbulence that interfere with the path of starlight. One of the most extreme examples of this occurs in deserts, where the ground heats dramatically during the day and cools rapidly at night. These sharp temperature shifts create powerful and chaotic air movements. Stargazing in a desert can be breathtaking because of the clarity of the sky, but it also can be filled with intense twinkling due to the strong variations in air density. Even something as seemingly gentle as a breeze can affect the twinkling of stars. Winds carry these layers of air at different speeds and directions, introducing additional instability. When you look up at the stars on a windy night and notice them twinkling more vigorously than usual, it is often because those moving air masses are creating ever-changing temperature boundaries, and with them, ever-shifting pathways for the starlight to travel through. The science of how light behaves in different mediums has been studied for centuries. One of the most fascinating outcomes of this research is the realization that even tiny differences in air temperature, just a few degrees, can bend light in measurable ways. This means that the atmosphere does not need to be in a stormy uproar for stars to twinkle. Even on calm nights, there is enough subtle variation in air density to disturb the precise path of starlight. What makes this especially compelling is that these changes are happening just above our heads. Most of the twinkling effect occurs within the first 10 to 20 kilometers of the atmosphere, where most of the air's mass resides. This layer is called the troposphere, and it's the same region where weather occurs, where clouds form, winds blow, and storms build. The chaotic nature of this region means that no two stargazing nights are ever exactly the same. One night, the stars may twinkle gently and rhythmically. Another night, they may shimmer rapidly, almost in a strobe-like fashion, as though the sky itself is unsettled. And yet, despite all this complexity, the result is beautifully simple to our eyes. We see a star gently flicker, and we feel something ancient and familiar, a sense of wonder, of smallness, of connection to the vast unknown. But behind that flicker is a story of thermal chaos, of layers of air shifting and tumbling in invisible patterns, all conspiring to take a steady beam of ancient starlight and turn it into a living dance. So the next time you look up and see a star twinkling in the night, think of the layers upon layers of warm and cool air through which that light has passed. Think of the invisible eddies and streams that have bent it this way and that, shaping it not with intention, but with the natural rhythm of Earth's breath. The atmosphere may obscure the perfect clarity of the stars, but it does so in a way that gives them life, offering us not only a glimpse into the cosmos, but a quiet, flickering reminder of the forces at work in the very air we breathe. Imagine a beam of starlight travelling through the vast, empty stretches of space, untouched and undisturbed, for perhaps thousands or even millions of years. During this immense journey, the photons, the tiny particles of light, maintain a nearly perfect trajectory, travelling in a straight line, pure and unwavering through the cold vacuum. But as these ancient photons finally approach Earth and reach the thin veil of our atmosphere, their journey becomes instantly more complex. They encounter a world of continual motion and subtle chaos, our dynamic, ever-changing atmosphere. Here, in this brief, final moment of their cosmic journey, the photons experience something entirely different: continuous refraction. Refraction is, at its essence, the bending of light as it moves from one medium to another. While it sounds simple enough, refraction at the atmospheric scale becomes an intricate dance, unfolding endlessly and unpredictably. To picture this clearly, envision yourself standing on the edge of a still pond. You drop a stone into the water, and ripples spread outward in gentle rings. If you look down through the water at an object resting on the bottom, you'll notice that its image shifts and distorts slightly with every ripple that passes. Each ripple is changing how the light moves from the object to your eyes, bending it differently moment by moment. Now imagine that same scenario, but amplified exponentially. Rather than a few ripples, there are countless tiny turbulent waves continually forming, intersecting, and colliding. The result would be a continually shifting, dancing, distorted image of anything beneath the water. That's precisely what happens to starlight as it passes through Earth's atmosphere. But instead of water waves, the waves are currents of air. Layers of varying temperature, density and motion that bend the starlight continuously and unpredictably. This continuous bending, this refraction in motion, occurs because air isn't uniform. It never sits still. Instead, it's made up of countless parcels of air, each at slightly different temperatures, pressures, and densities. Even slight temperature variations cause significant differences in how much each layer bends the incoming starlight. Warm air, less dense and lighter, refracts light differently than cooler, denser air. As starlight passes rapidly through these countless microscopic variations, the path of the photons is repeatedly adjusted. This bending isn't a single event, but rather a constant, ongoing process. As each photon moves downward toward Earth, it encounters not one, but hundreds or even thousands of these microenvironments, each slightly shifting its trajectory. These shifts are incredibly subtle, but occur at such rapid speeds and frequencies that the starlight reaching our eyes appears to dance or flicker. It's critical to understand that these tiny bends occur continuously, changing from moment to moment as air masses move. When observing a star, you're not seeing a static, single line of light. Instead, you're seeing an ever-changing line, a rapid, fluid movement of photons that your eye and brain interpret as flickering. What might seem random or chaotic is actually a beautifully complex interaction between light and air, physics and motion, energy and matter. One of the most remarkable things about this continuous refraction is the speed at which it happens. Changes in atmospheric conditions are occurring at such rapid rates, often multiple times per second, that your eyes perceive a constant shimmer. Stars don't twinkle slowly. They flicker rapidly, sometimes dozens or even hundreds of times per minute. This rapid flickering is a direct reflection of the atmospheric turbulence that is continually reshaping the path of the incoming starlight. Another fascinating aspect of this continuous refraction is that it's not uniform across the sky. Stars near the horizon, where their light must pass through more air layers, twinkle more intensely than stars overhead. The longer the journey through Earth's atmosphere, the more numerous and intense the interactions become. Near the horizon, starlight must travel through layers upon layers of air, each with its distinct temperature, density and turbulence. Each additional layer multiplies the tiny adjustments to the light path, creating a more vigorous, pronounced twinkle. Moreover, this continuous bending doesn't only shift the apparent position and brightness of the star, it can also briefly alter the perceived colour of starlight. The atmosphere's varying density and temperature layers also separate the incoming starlight into its constituent colours. Each colour, or wavelength, bends slightly differently. Shorter wavelengths like blue refract more strongly than longer wavelengths like red. As these photons shift slightly in different directions due to continuous refraction, the starlight occasionally appears to flash subtly different colours: red, blue, green or yellow, adding an ethereal beauty to the phenomenon we observe. Refraction in motion also has practical implications for astronomers. The constantly shifting path of starlight, while beautiful to the casual observer, poses significant challenges for astronomical observation. Precise measurements require stable, undisturbed images, but the atmosphere's continuous refraction introduces uncertainty and blurriness. To combat this, astronomers utilize specialized techniques and technologies, such as adaptive optics, which actively compensate for atmospheric turbulence in real time, restoring clarity to telescopic images. Adaptive optics systems continuously measure atmospheric distortion by tracking how reference stars or artificial laser guide stars shift position in real time. Tiny mirrors in telescopes are then subtly adjusted hundreds of times per second to counteract the bending caused by atmospheric turbulence, effectively undoing the continuous refraction. This technology has dramatically improved the quality of ground-based astronomy, allowing us to peer deeper into space than ever before, despite Earth's ever-moving atmosphere. Finally, it's worth reflecting on the profound simplicity hidden within this complexity. Continuous refraction in motion is just air interacting with light. A fundamental interaction happening countless times each second, all around us, invisible yet ever present. Each flicker, each sparkle of a star is evidence of Earth's dynamic atmosphere, a constant reminder that our planet breathes and moves, even in the silence of the night. Stars twinkle because Earth's atmosphere is alive with motion, never static, always reshaping the cosmic signals sent to us from distant worlds. So next time you gaze up at the night sky and watch stars flicker and dance, know that you're seeing not just distant suns, but also the invisible breath of our atmosphere, a ceaseless, continuous dance between light and air, forever shaping the way we perceive the universe. At the heart of the gentle dance we see when stars appear to flicker in the night sky lies a scientific phenomenon with an elegant name: scintillation. Scintillation is more than just a fancy term for twinkling. It captures the subtle yet complex physical processes responsible for the rhythmic, flickering brightness that gives stars their characteristic shimmer. To truly grasp why stars scintillate, and why this process holds such fascination for astronomers and casual stargazers alike, we must journey into the precise physics that transforms stable starlight into a mesmerizing display of cosmic choreography. Scintillation refers explicitly to the rapid fluctuations in brightness and colour that occur when starlight passes through Earth's turbulent atmosphere. These fluctuations are caused by continual shifts in the refractive index of air along the starlight's path. The refractive index describes how much a material bends or slows down light. It varies slightly, but constantly within our atmosphere, because of temperature, density and humidity changes. As starlight moves swiftly through these invisible, ever-changing layers, each tiny variation causes subtle adjustments in the path of the photons, tiny adjustments that our eyes detect as a star's flickering. What makes scintillation particularly fascinating is how delicately balanced it is. Each small shift, each microscopic change in air, density or temperature, only bends the incoming light by a fraction of a degree. Individually, these bends would be nearly impossible for our eyes to detect. But collectively, across the vast stretch of atmosphere, hundreds or thousands of these tiny bends happen every second. Together they form a continuous series of minute distortions, and it is this rapid succession that we perceive as scintillation. This process is dynamic, continuous, and incredibly fast-paced. It is not just a few isolated fluctuations occurring occasionally. Rather, scintillation is happening relentlessly and ceaselessly many times per second. Because our eyes can't resolve each individual shift in the path of the starlight, we see them blended together into a continuous, rapid shimmer. This speed gives scintillation its distinctive quality, appearing like a delicate, persistent flutter, rather than a slow, gradual flicker. Moreover, scintillation does more than simply affect brightness. It can also introduce brief, fleeting changes in colour. The reason lies in how air refracts different wavelengths of light differently, a phenomenon known as chromatic dispersion. Blue and violet light, having shorter wavelengths, bend slightly more than red or yellow light. When atmospheric turbulence briefly separates these colours as starlight passes through a turbulent pocket of air, the star might momentarily flash subtle shades of red, green or blue. While these shifts are typically fleeting and subtle, occasionally they can become strikingly visible, especially when viewing bright stars low on the horizon. These vivid, colourful twinkles have inspired generations of skywatchers to describe stars as glittering gems suspended in the heavens. The intensity of scintillation is strongly influenced by the angle at which starlight enters Earth's atmosphere. Stars directly overhead, whose light takes the shortest possible path through our atmosphere, generally exhibit minimal scintillation. However, stars lower toward the horizon must traverse significantly greater lengths of atmospheric layers, passing through more regions of turbulence and temperature variation. Consequently, these stars experience greater scintillation, often dramatically so, as anyone who has watched a star rise or set near the horizon knows well. Observing this effect clearly reveals the direct relationship between scintillation and atmospheric path length. Atmospheric scintillation also varies with local weather conditions and environmental factors. On cold, clear nights, particularly after a warm day, temperature gradients in the atmosphere are sharper, leading to more pronounced turbulence. This causes stars to scintillate more intensely. Conversely, stable atmospheric conditions, such as those found at high altitudes or during consistent weather patterns, typically produce minimal scintillation. Astronomers refer to these stable periods as having good seeing conditions. crucial for making precise astronomical observations and obtaining clear telescopic images. But scintillation isn't just an observational curiosity, it also has meaningful implications for astronomy. Before adaptive optics and space telescopes, astronomers grappled constantly with the challenges scintillation posed to their research. Fluctuating brightness and image distortions limited their ability to precisely measure stellar properties or clearly resolve distant cosmic phenomena. To address these problems, modern astronomy has developed powerful tools like adaptive optics. By using sophisticated instruments that continuously monitor how a star's image is distorted by scintillation, telescopes can instantly correct for those distortions, dramatically improving image quality. This remarkable technology allows astronomers to neutralize atmospheric turbulence, turning blurry, twinkling starlight into stable, razor-sharp images. Historically, scintillation has also guided practical human activities. Sailors and explorers navigating by stars learned to interpret scintillation as a subtle indicator of impending weather changes. Increased or rapid scintillation could signal approaching storms, changing temperatures, or shifting wind patterns. Farmers, too, learned that unusually intense star twinkling often predicted weather changes, becoming a reliable and subtle indicator for planting, harvesting, or taking precautions against adverse weather. Interestingly, scintillation is not unique to starlight or Earth's atmosphere. Any environment through which light travels, whether planetary atmospheres or even cosmic gas clouds, can produce scintillation effects if the medium is turbulent or varied enough. Astronomers studying radio waves from distant quasars, for instance, often observe scintillation when signals pass through interstellar clouds. Understanding scintillation thus provides insights not only into Earth's immediate surroundings, but also into distant cosmic phenomena, offering astronomers valuable clues about conditions in far-flung corners of the universe. At its heart, scintillation is a beautiful illustration of complexity emerging from simplicity. It is simply light bending as it moves through air. But the infinite variability, subtle interplay of physics, and rapid movement transform this simple concept into an endlessly intricate phenomenon. Each tiny adjustment, each subtle atmospheric shift, contributes to a celestial dance that captivates our imagination every night. To observe scintillation is to witness physics in real time, a direct visualization of turbulence and tranquility, of chaos and order, in constant interaction. So next time you gaze upwards and notice a star's gentle flicker, take a moment to appreciate the vast complexity behind that simple, rhythmic sparkle. Scintillation is not just twinkling. It is a living demonstration of how our dynamic atmosphere interacts with ancient cosmic light, transforming the night sky into a quietly mesmerizing display that reminds us of the subtle forces constantly at work around us. When you stand beneath the vast, open night sky, one of the most subtle yet fascinating phenomena you might notice is that some bright objects, particularly planets, shine steadily while most stars dance and flicker. This difference, so subtle at first glance, yet profound upon deeper reflection, is rooted in the intricate relationship between how we perceive these distant objects and the physical properties that determine their appearance from our perspective here on Earth. To truly understand why planets shine calmly and steadily while stars twinkle, we must explore an essential distinction in astronomy. The difference between objects that are effectively point sources of light and those that are extended sources. Stars, despite their colossal physical sizes, appear from Earth as tiny points of light. The vast distances separating us from even the nearest stars are so immense that their enormous sizes shrink down from our vantage point to single infinitesimal points. In fact, even the largest and brightest stars, like Sirius or Vega, appear as mere pinpricks of brilliance in our night sky. Because they appear as single, point-like beams of light, their image can be easily disrupted by even the slightest atmospheric turbulence. Any shift or distortion in that single, delicate ray of starlight dramatically changes how we perceive the star's brightness and position, making it appear to flicker and dance unpredictably. Planets, however, differ significantly in their apparent appearance. Although planets like Venus, Mars, Jupiter, and Saturn are still incredibly distant, millions of kilometers away, they are substantially closer to us than stars, which are light years away. This relative proximity means planets have an actual, measurable angular diameter when viewed from Earth. Unlike stars, planets do not appear as perfect points. They have dimension, presenting themselves as tiny disks of reflected sunlight rather than single rays of direct starlight. While their disks are extremely small, so small in fact that they typically appear star-like to the unaided human eye, they are large enough to make a crucial difference when viewed through Earth's turbulent atmosphere. Consider the process of atmospheric turbulence again. As light passes through Earth's constantly moving air, it bends and refracts continuously, creating rapid and unpredictable changes in direction. For stars, this bending affects their singular point of light completely, causing noticeable shifts that appear to our eyes as dramatic changes in brightness and position. This is why stars twinkle. Planets, with their tiny but measurable disks, offer a subtly different scenario. The disk of a planet presents multiple, distinct paths of light entering our atmosphere simultaneously. While one area of the disk may be disturbed or refracted differently by a turbulent air pocket, another part might remain relatively unaffected or refracted in a slightly different direction. Crucially, these slight variations in atmospheric refraction tend to average out across the planet's disk, creating a much steadier, less volatile appearance overall. Imagine holding a small flashlight and shining its beam through a window covered in uneven, rippling glass. The narrow beam of light would be distorted considerably, shifting erratically, much like the twinkle of starlight through turbulent air. But if you replace that flashlight with a larger lamp, spreading the beam over a wider area, the rippling window glass would distort parts of the beam in different directions. As a result, the overall illumination would appear more uniform, calmer, and steadier. The planet's small disk behaves just like this broader beam, resisting atmospheric turbulence and thus avoiding intense twinkling. The effect is subtle enough that, to the naked eye, planets appear steadier, calmer, and more stable, making them stand out among their stellar neighbours. Indeed, amateur astronomers and seasoned skywatchers have long used this steady, unblinking appearance as a practical way to distinguish planets from stars, even without telescopic equipment. On clear nights, planets like Jupiter or Saturn shine with a steady, regal glow, offering a calm, reassuring presence amid the flickering stars. However, planets are not immune entirely to twinkling. Under certain circumstances, even planets can shimmer slightly. When planets sit very low on the horizon, their light must traverse much longer paths through Earth's atmosphere. In these cases, even the modestly extended disk of a planet isn't sufficient to fully counteract atmospheric turbulence. Consequently, planets near the horizon may appear to gently twinkle, flicker, or shimmer briefly, particularly when viewed across vast distances and through particularly turbulent air layers. Nonetheless, even in these cases, their twinkle is generally softer, less rapid, and less pronounced than stars. Astronomers have leveraged this distinct difference extensively. For precise astronomical observations, identifying point sources versus extended sources is vital. Understanding why planets resist twinkling better helps astronomers carefully calibrate their instruments and observations. They know that point sources, like stars, will always be more significantly affected by atmospheric conditions, requiring sophisticated technology, such as adaptive optics, to correct atmospheric distortions and restore clarity. Extended sources like planets, moons, and even certain nebulae or distant galaxies appear more stable and require different observational techniques, but they also allow astronomers to measure and observe subtle planetary features more reliably. Interestingly, the concept that planets appear steadier also ties into human history and culture. Ancient sky watchers recognized that certain bright lights in the sky, wandering stars as they were known, were special because they moved against the background stars and appeared steadier. This steady brightness gave planets symbolic importance in mythology and astrology, embodying stability, regularity, and predictability. Their lack of twinkling became part of their identity and meaning in human storytelling and spirituality, influencing civilizations from the Babylonians and Egyptians to the Greeks and Romans, who saw planets as powerful symbols precisely because of their steadfast appearance in the night sky. This distinction between stars and planets also helps remind us of our perspective within the cosmos. The reason planets do not twinkle as stars do is fundamentally about our place in space. Planets are our neighbours in a shared solar system, visible as actual physical bodies, each reflecting sunlight back to us. Stars, though many vastly larger than planets, are unimaginably distant suns, their vast distance reducing them to mere points of flickering light through our turbulent atmosphere. Each time we see a planet shining steadily amid twinkling stars, we are subtly reminded of our proximity to these worlds, of the cosmic neighbourhood we inhabit, and of the vastness separating us from the distant stars beyond. Ultimately, the difference between twinkling stars and steady planets is a beautiful interplay of geometry, distance, optics, and the physics of light. The fact that planets appear steady, calm and tranquil amid the shimmering stars serves as both a practical tool for astronomers and a poetic reminder for us all. Every glance skyward reveals something profound, not just about the universe beyond our planet, but about our own position within the cosmos, our perception, and the subtle yet powerful ways in which the physical world shapes what we see. One of the most intriguing and easily observed aspects of star twinkling is how dramatically the effect intensifies as stars approach the horizon. Stars positioned directly overhead generally exhibit only gentle twinkling, quietly shimmering with an occasional flicker. But stars closer to the horizon appear to dance, flash and sparkle energetically, often changing colours rapidly and vividly. To understand why altitude matters so profoundly, in the intensity of stellar twinkling, we must explore the intricate relationship between the length of a star's atmospheric journey and the degree of turbulence encountered along the way. Imagine standing beneath a deep, dark, star-filled sky, gazing directly upward toward a star near the zenith, the point directly overhead. The starlight you're seeing travels the shortest possible path through Earth's atmosphere, typically less than 100 kilometers thick. Though still subject to some atmospheric turbulence, the journey is relatively short, limiting the number of air pockets and temperature variations the starlight encounters. The resulting refraction and scintillation are mild, causing only subtle, gentle flickers. The zenith, therefore, provides the clearest, most stable view of the cosmos, minimizing twinkle and allowing astronomers and sky watchers alike to perceive stars with relative clarity. Now shift your gaze downward toward the horizon, toward a star just rising or setting. The starlight coming from these low altitude stars must pass through a significantly longer path through Earth's atmosphere, often hundreds of kilometers more than stars overhead. This extended path dramatically increases the number and intensity of turbulent air layers the light encounters. Each pocket of air, each layer of varying temperature or density, refracts and bends the starlight slightly. When multiplied by hundreds or thousands of these subtle interactions, the cumulative effect transforms the star's once stable beam of light into a rapidly flickering, shifting, and colour-changing spectacle. To visualise this effect, imagine a clear, still lake. If you look straight down through calm water, you'll see an object clearly and steadily beneath the surface. Now, look at the same object at a shallow angle from a distance across the lake. The light reflecting off, or travelling through the water from this low angle, encounters far more disturbances. Ripples, waves, even tiny variations in water temperature. The object seen through this longer, shallower path becomes distorted, shimmering and shifting constantly. The star's path through Earth's atmosphere operates under precisely the same principle. Longer paths equal more atmospheric interactions, dramatically intensifying twinkling. Additionally, the atmosphere itself changes significantly near the horizon. The lower atmosphere, close to Earth's surface, is denser, more humid, and more prone to rapid temperature variations than higher altitudes. These conditions enhance refraction and turbulence. Near the horizon, the atmosphere may contain localized temperature inversions, layers of warm air sitting above cooler air, which produce highly turbulent refraction conditions. This intensified turbulence near Earth's surface further magnifies the twinkling effect, making stars near the horizon appear to flash vigorously, often changing colours vividly from blue to red to green in quick succession. Indeed, the colour shifts observed at low altitude provide a spectacular display of a phenomenon known as atmospheric dispersion. Dispersion occurs because different colours, wavelengths, of starlight refract at slightly different angles. Shorter wavelengths, such as blue and violet, refract more strongly than longer wavelengths like red and yellow. When starlight passes through extended turbulent paths near the horizon, these subtle differences in refraction become pronounced, briefly separating colours and causing the star to flash rapidly and dramatically from one colour to another. To observers, These flashing colours can appear almost magical, transforming stars into sparkling, jewel-like points of shimmering brilliance. The phenomenon of enhanced twinkling near the horizon is not merely visually stunning, it also significantly impacts astronomical observations. Professional astronomers intentionally avoid observing celestial objects near the horizon whenever possible. Observatories are typically placed at high altitudes, precisely to minimize atmospheric interference and limit the extent of turbulent air through which starlight must travel. Observing closer to the zenith yields significantly clearer, more stable images, essential for precise measurements and detailed scientific research. Nevertheless, astronomers sometimes intentionally study objects near the horizon. These challenging observations can provide valuable insights into Earth's atmosphere itself. By analysing how starlight is refracted and scattered at low altitudes, astronomers can study atmospheric structure, temperature gradients, humidity variations, and turbulence patterns in detail. Such research is critical not only for astronomical purposes, but also for understanding atmospheric dynamics more broadly, influencing weather prediction, climate studies, and even the development of improved optical technologies on Earth. Additionally, historical navigators and early astronomers often relied on low-altitude star observations, despite their challenges. Mariners, explorers, and ancient civilizations tracked celestial objects near the horizon to determine precise geographical positioning, date seasonal changes, and make calendar predictions. The pronounced twinkling, though problematic for precise astronomical measurements, also served as practical indicators. Intense twinkling near the horizon was frequently interpreted as a sign of impending weather changes, storms, or shifting atmospheric conditions. Such observations became part of navigational lore, embedded deeply in cultures worldwide, linking astronomy, meteorology, and human history in profound ways. Culturally and poetically, the spectacular twinkling near the horizon has always held special fascination. The dramatic flickering and colourful scintillation seen as stars rise or set has inspired poets, philosophers, artists, and dreamers across countless generations. They interpreted these dancing, sparkling stars as symbols of change, transformation, mystery, or divine communication. This phenomenon added a rich layer of symbolism and beauty to our collective perception of the night sky, enhancing humanity's enduring emotional and imaginative connection with the cosmos. Thus, the dramatic enhancement of stellar twinkling near the horizon emerges from a complex interplay of physics, atmospheric science, astronomy, history, and culture. Altitude profoundly matters because it determines the length of atmospheric interaction, the intensity of atmospheric turbulence, and the degree of colour dispersion, all contributing powerfully to how vividly a star twinkles. Far from being a trivial curiosity, this effect encapsulates the intricate beauty of Earth's atmospheric dynamics and provides endless fascination for observers from ancient times to the modern era. The next time you gaze toward a star twinkling vibrantly near the horizon, remember you are witnessing an extraordinary journey. Ancient photons traversing an immense, turbulent ocean of air, constantly shifting, refracting, and dispersing. You are seeing physics in action, history in motion, and poetry unfolding in real time. An ephemeral, shimmering dance, bridging earth, sky, and imagination in a delicate, luminous spectacle. When you step outside to gaze at the stars, one of the first things you might notice, if you watch closely, is that the sky never looks exactly the same from one night to the next. Sometimes stars appear calm, steady and clear, shining gently and rhythmically with minimal flickering. On other nights, the stars sparkle vigorously, twinkling intensely, almost as though the heavens themselves are excited. This variability from night to night is a subtle but powerful reminder that our atmosphere is dynamic, always shifting and changing, profoundly influencing the way we see the stars. But what exactly causes this night-to-night variability in how much stars twinkle? To fully understand this fascinating aspect of stargazing, we need to delve into atmospheric dynamics, weather conditions, seasonal changes, and even local environmental factors, all of which contribute profoundly to the nightly dance of the stars. One primary factor behind this variability is atmospheric turbulence, rapid, chaotic movements of air driven by temperature differences, pressure variations, and winds at various altitudes. Turbulence occurs constantly, but its intensity fluctuates dramatically depending on local weather. On nights when the air is calm and stable, atmospheric turbulence is minimal. This calm air is characterized by fewer and gentler temperature gradients, meaning less refraction, less distortion of starlight, and consequently less intense twinkling. Such nights are prized by astronomers, known as nights of excellent seeing conditions. The stars appear steadier, allowing clearer and more precise observations, whether with telescopes or the naked eye. In contrast, turbulent weather conditions significantly enhance twinkling. Consider a warm summer day transitioning into a cooler night. As the sun sets, the ground quickly cools, creating sharp temperature differences between lower atmospheric layers close to the Earth and higher, warmer layers above. This sharp temperature gradient generates powerful vertical currents, rapidly rising warm air pockets and descending cooler air that significantly increase atmospheric turbulence. The turbulence generated by these rapid vertical air movements dramatically intensifies the twinkling of stars, making them appear to flash, flicker, and shimmer energetically. Wind speed and direction also play a crucial role. On windy nights, particularly when winds at different altitudes blow at varying speeds or directions, turbulence is heightened considerably. These differences in wind conditions create chaotic mixing of air layers, each layer potentially differing in temperature and density. Starlight passing through this rapidly mixing, turbulent air experiences constant shifts in refraction, causing intense and rapid twinkling. Thus, a windy night can transform a usually calm and gentle star into an energetic, rapidly flickering point of light. Humidity and moisture levels further influence how stars twinkle. On nights with high humidity, the air contains substantial amounts of water vapor. Moist air has different refractive properties compared to dry air, especially when temperature gradients are pronounced. High humidity can enhance atmospheric turbulence and amplify refraction effects, leading to more pronounced twinkling. Foggy or misty conditions, though often obscuring clear views of stars altogether, can intensify the twinkling of any visible stars due to the complex interplay between moisture and air density. Seasonal changes also introduce variability in nightly star twinkling. In winter months, colder, denser air settles closer to the ground, creating relatively stable atmospheric conditions during clear, calm nights. Stars on these crisp, clear winter evenings often appear steady and bright, twinkling minimally. Conversely, spring and autumn, transitional seasons characterized by rapid temperature fluctuations, frequently bring more turbulent conditions. Rapidly shifting temperatures, warm days followed by abruptly cooler nights, significantly enhance atmospheric turbulence, causing stars to twinkle more intensely during these seasons. Even local geography influences nightly variability in star twinkling. Mountainous regions, valleys, coastlines, and open plains all produce unique local atmospheric conditions. Mountains can create turbulent airflows as wind moves rapidly over peaks and ridges, stirring up localized turbulence. Valleys might trap cooler air beneath warmer layers, forming temperature inversions and localized turbulence. Coastal regions, with their significant differences in land and ocean temperatures, produce distinctive, rapidly changing atmospheric conditions that significantly influence star twinkling intensity from night to night. Human activity and environmental factors also subtly influence atmospheric turbulence. Urban areas, filled with concrete, pavement, buildings and vehicles, retain heat longer after sunset, creating sharp thermal contrasts with cooler air above. This urban heat island effect can significantly increase turbulence, causing stars seen from cities or suburbs to twinkle more energetically than those observed from rural areas with less artificial heat retention. Astronomers keenly understand these nightly variations as they directly affect the quality of their observational data. Observatories track seeing conditions meticulously, assessing nightly atmospheric turbulence and clarity using specialized instruments like seeing monitors and laser-guided adaptive optics systems. Adaptive optics, which measure atmospheric turbulence in real time and dynamically adjust telescopic mirrors to counteract it, allow astronomers to observe clearly even under variable conditions. Yet nights with minimal twinkling, those rare moments of exceptional seeing, remain particularly valuable for obtaining pristine astronomical data. Interestingly, historically, humans have observed these nightly variations in twinkling for practical reasons too. Sailors, farmers, and indigenous peoples have long used changes in twinkling intensity as informal weather forecasts. An increase in twinkling could signal impending storms, shifting wind patterns, or temperature changes. Such knowledge was crucial, guiding decisions about sailing, farming, hunting, and other essential activities. Star twinkling thus became embedded deeply into folklore and traditional knowledge, intimately connecting astronomy, meteorology, and human culture. This nightly variability in star twinkling also possesses poetic and philosophical dimensions. It reminds us that the universe, though vast and seemingly constant, interacts closely and constantly with our immediate surroundings. Every flicker and shimmer in the stars is a subtle record of Earth's shifting weather and atmospheric dynamics. Nature's gentle reminder of our planet's endless cycles of change. This variability invites contemplation, encouraging us to look closely, notice subtle differences, and marvel at the interplay between distant cosmic light and the restless air enveloping our world. So the next time you step outside and look upwards, pay careful attention to how the stars are twinkling tonight. Notice their intensity, rhythm and colour. Think about the invisible air around you. Warm air rising, cool air sinking, winds blowing gently or fiercely, moisture invisibly suspended above. Every subtle change in star twinkling tells you something real about the invisible world surrounding you. A hidden dance of atmospheric currents and temperature variations shaping your view of the universe. The nightly variability of star twinkling thus becomes not merely an observation, but a profound, living connection between Earth, sky, and observer. Always changing, always fascinating, always worth noticing. When gazing at the night sky, especially from urban or suburban areas, you may notice something subtle yet deeply impactful. The stars don't appear quite as vividly. Their twinkling not as clearly defined as it is in more remote, darker locations. This subtle phenomenon is caused by something astronomers and environmental scientists call light pollution, a significant factor that subtly but profoundly influences how we perceive the stars and their characteristic twinkling. While atmospheric turbulence is the primary driver behind the twinkling of stars, the presence of artificial lights and atmospheric particulates often modifies, diminishes, or alters how clearly we perceive this gentle cosmic flicker. Light pollution is the excess artificial illumination from urban environments, streetlights, buildings, vehicles, billboards, that scatters upwards into the atmosphere. This artificial glow not only obscures our view of the stars themselves, but also subtly changes the conditions under which we observe atmospheric scintillation. By creating a brighter sky background, light pollution reduces the contrast between stars and the surrounding sky. This reduction in contrast often diminishes the perceived intensity and beauty of star twinkling, softening, or even masking the delicate fluctuations in brightness and colour that make stars appear alive with motion. Imagine standing in a brightly lit city or suburban neighbourhood at night. The sky above isn't truly dark. Rather, it has an almost orange, milky or hazy glow. This background illumination significantly impacts your ability to notice subtle fluctuations in starlight. Because stars twinkle due to subtle and rapid shifts in brightness, a brightened background masks many of these small variations. The contrast needed to see the delicate dance of atmospheric scintillation clearly is significantly reduced, causing the stars to appear duller, less dynamic, and less vividly alive. In essence, stars might still twinkle, but your eyes struggle to distinguish the twinkling clearly against a brighter, artificially illuminated sky. Moreover, artificial lights don't simply illuminate. They interact dynamically with atmospheric particles, amplifying the issue. Urban areas are filled with tiny airborne particulates such as dust, soot, pollutants, smoke, and moisture droplets. Artificial lighting scatters off these tiny particles, creating what is known as sky glow, a diffuse glow over cities and suburbs. This scattering process reduces atmospheric transparency, creating a hazy layer through which starlight must pass. As starlight travels through this particulate-filled air, it is weakened, scattered, and diffused. The combined effect of scattering and reduced transparency not only dims stars, but also subtly smooths out their twinkle, muting the delicate fluctuations caused by turbulence and refraction. In heavily polluted areas, stars might appear steady, dull, or barely visible, their vibrant twinkling almost entirely lost. This smoothing effect of urban haze is intriguing because paradoxically, it might initially seem beneficial. After all, less twinkling means steadier looking stars. But for astronomers and sky enthusiasts, the result is deeply detrimental. The subtle flickers and colour variations lost in urban haze contain important observational information about atmospheric conditions and the stars themselves. Without clearly observable scintillation, we lose both scientific insights and the simple joy of stargazing's inherent beauty. Interestingly, the effect of light pollution on twinkling can vary depending on specific urban conditions and environmental factors. On humid or foggy nights, urban light pollution can create an even more pronounced sky glow, scattering broadly and creating a thicker, more opaque atmospheric veil. Under these conditions, stars become nearly invisible, their gentle twinkle completely obscured. Conversely, during clearer nights with less humidity or fewer airborne particulates, the effects of urban sky glow may be less pronounced, allowing some twinkling to remain visible, though still diminished compared to darker rural skies. Seasonal factors can also amplify or mitigate the effects of light pollution on twinkling. In winter months, especially in colder climates, air tends to be clearer, with fewer particulates, pollutants, or humidity, conditions that reduce sky glow and slightly improve stargazing even in urban settings. During warmer months, however, increased humidity, dust and pollution often create thicker atmospheric conditions, exacerbating light pollution and significantly diminishing visible twinkling. Local geography plays yet another crucial role. Cities surrounded by mountains, hills, or valleys may experience localized concentrations of atmospheric particulates and pollutants trapped by geographic features. These conditions enhance sky glow dramatically, especially in valleys or basins, causing star twinkling to be significantly muted or entirely obscured. In contrast, coastal cities, or those near large bodies of water, may experience clearer atmospheric conditions, as breezes or oceanic currents often help disperse particulates and pollutants, preserving a bit more twinkling clarity. Astronomically, the impact of light pollution goes beyond mere aesthetic loss. For professional astronomers, urban sky glow and atmospheric haze severely limit observational capabilities, prompting the relocation of observatories to remote areas far removed from urban illumination. Precise astronomical observations, whether studying distant galaxies or nearby celestial objects, require dark, clear skies and minimal artificial interference. Observatories in remote deserts, mountains, or islands, such as those in Chile, Hawaii, or the Canary Islands, are strategically placed to minimize urban sky glow and atmospheric pollution, preserving the pristine twinkling necessary for accurate scientific observation. Beyond astronomy, the subtle loss of twinkling due to light pollution has profound cultural and psychological implications. Throughout history, the gentle flicker of stars has inspired poetry, art, mythology, spirituality, and philosophical reflection. The subtle twinkle symbolizes wonder, mystery, and connection with the cosmos. As urban sky glow diminishes our ability to perceive these delicate fluctuations clearly, we lose not only a practical astronomical phenomenon, but also a deeply symbolic and emotional aspect of human experience. our direct and tangible connection with the beauty and mystery of the universe. Fortunately, awareness of light pollution and its impact is growing, leading to global efforts aimed at reducing unnecessary artificial illumination. Initiatives such as dark sky movements, the adoption of lighting technologies designed to minimize upward scattering, and community-driven efforts to reclaim the beauty of the night sky are helping restore some of the clarity and wonder once commonplace to stargazers everywhere. Reducing artificial sky glow not only helps preserve astronomical observation, but also revitalizes our emotional and spiritual connections to the cosmos. Next time you gaze upward, take a moment to reflect on the subtle yet powerful influence of human-made light on your view of the stars. Recognize that each diminished twinkle carries a message, one about our environment, our choices, and our ability to appreciate the delicate natural interplay between earth and sky. By understanding and addressing the impact of light pollution, we reconnect with something fundamental, our place beneath a star-filled sky, one that twinkles clearly, vividly and beautifully, just as it has done for countless generations before us. On certain clear nights, particularly when the air is turbulent and stars are near the horizon, you might notice a captivating phenomenon. Stars don't merely flicker gently, they also appear to flash distinct colours, red, blue, green, orange, rapidly and vividly. This vibrant colour-changing effect transforms stars into sparkling celestial jewels, vividly dancing in a rhythmic ballet of colours. To fully appreciate and understand why some stars twinkle in this dramatic, colourful way, we must explore a remarkable optical phenomenon called atmospheric dispersion. Atmospheric dispersion arises from the simple yet powerful physical fact that different colours of light, which correspond to different wavelengths, bend slightly differently as they pass through our atmosphere. Blue and violet wavelengths, shorter wavelengths, refract more strongly than longer wavelengths like red, orange or yellow. When starlight travels through Earth's turbulent atmosphere, each wavelength encounters slightly different refractive conditions, causing the incoming white starlight to separate briefly into its component colours. The greater the atmospheric turbulence, and the longer the atmospheric path, as is the case near the horizon, the more pronounced this dispersion becomes, resulting in vivid, rapid colour changes. To visualise how this works, imagine shining a beam of white light through a glass prism. The prism refracts, or bends, the incoming white light, separating it into a clear spectrum of colours, forming a miniature rainbow. Our atmosphere acts like countless microscopic prisms created by pockets of air at varying temperatures and densities. Each of these microscopic atmospheric prisms refracts starlight differently, dispersing colours in slightly different directions. As atmospheric turbulence rapidly shifts these miniature prisms, the separated colours continuously blend, separate, and blend again, creating a star that appears to flash rapidly and vividly from red to blue to green and back again. This colourful scintillation is particularly pronounced for bright stars located near the horizon. Stars at low altitudes must traverse much thicker layers of atmosphere, encountering countless additional air pockets and miniature prisms along the way. Each additional layer increases the degree of dispersion, making colour shifts far more noticeable and dramatic. For example, Sirius, the brightest star in the night sky, is well known for its spectacular, multicoloured twinkling when viewed low on the horizon. observers frequently report seeing flashes of red, blue, green, and even purple, a dazzling cosmic light show created solely by atmospheric dispersion and turbulence. Interestingly, not all stars exhibit equally vivid colour changes. Several factors influence how vividly a star appears to shift colours, including its brightness, its spectral type, the inherent colour of the star itself, and local atmospheric conditions. Bright, bluish-white stars like Sirius or Vega often display particularly striking colour shifts, because their intense brightness and broad spectrum of emitted wavelengths highlight atmospheric dispersion more dramatically. Conversely, stars that are inherently redder or less bright, such as Betelgeuse or Aldebaran, still twinkle colourfully, but their colours tend to shift less noticeably, appearing mostly red or orange, occasionally flickering briefly to yellow or green. The inherent brightness and spectral colour of the star thus significantly influence how vividly its twinkling manifests. Local atmospheric conditions also profoundly impact colourful twinkling. Cold, clear nights with sharp temperature gradients between air layers enhance atmospheric dispersion effects, causing stars to twinkle with striking colour changes. Additionally, nights characterized by rapidly moving air masses or strong winds at varying altitudes increase turbulence, further intensifying dispersion. Humidity and particulate matter can either enhance or obscure these colourful displays. Moist air can intensify dispersion by altering the refractive properties of the atmosphere, creating even more dramatic colour shifts. Conversely, heavy haze, pollution, or excessive moisture can diffuse and soften colour shifts, diminishing the clarity and vibrancy of the twinkling colours. Seasonal variations also influence colourful star twinkling. Winter nights, particularly clear, crisp evenings following sunny winter days, often produce excellent conditions for vividly colourful twinkling. The sharp thermal contrasts typical of winter, very cold surface temperatures beneath relatively warmer upper air layers, generate pronounced atmospheric turbulence, maximising dispersion effects. Summer and spring months, with more uniform air temperatures and less intense atmospheric turbulence, may produce subtler, less vividly colourful twinkling. Observers can use colourful twinkling practically to gauge atmospheric conditions. Intense, colourful scintillation often signals significant atmospheric turbulence, indicating a possible shift in weather conditions, approaching storms, or changing wind patterns. Historically, sailors, farmers, and indigenous communities pay close attention to vividly twinkling stars as informal indicators of weather changes or atmospheric disturbances, embedding colourful twinkling deeply into navigational lore and weather prediction traditions. Astronomically, vividly twinkling stars near the horizon pose significant challenges. The constant, rapid shifting of colour and brightness severely complicates precise astronomical measurements. For example, professional astronomers carefully avoid observing celestial objects low on the horizon, precisely because colourful atmospheric dispersion greatly diminishes observational accuracy. Advanced telescopes often include sophisticated adaptive optics and atmospheric dispersion correctors, complex systems that precisely measure and counteract these colourful fluctuations, allowing astronomers to obtain accurate, clear, and stable observations even amid significant dispersion effects. However, colourful star twinkling isn't solely an obstacle for astronomers. It also provides valuable scientific insights. By carefully analysing the rapid colour changes of twinkling stars, atmospheric scientists can study subtle atmospheric conditions in remarkable detail. Dispersion patterns reveal intricate information about temperature gradients, turbulence intensity, wind velocities at different altitudes, and humidity variations. These insights have implications not only for astronomy, but also for meteorology, climate science, and even aviation safety, enhancing our overall understanding of atmospheric dynamics. Beyond the scientific realm, the colourful twinkling of stars profoundly enriches human culture and imagination. The mesmerising, jewel-like sparkle of vividly twinkling stars has inspired countless poets, artists, philosophers, and dreamers throughout human history. Stars flashing brilliant colours across the sky symbolise beauty, mystery, wonder, and cosmic connection. In mythology, vividly twinkling stars were often interpreted as celestial messages, omens, or spiritual signals from the heavens. In art and literature, the shifting colours evoke emotional depth and poetic imagery, embodying humanity's profound, emotional, and imaginative bond with the cosmos. Thus, the colourful twinkling of stars is far more than a mere optical curiosity. It embodies the intricate interplay of physics, atmospheric science, history, mythology, culture, and human imagination. Each flashing colour is a miniature symphony of scientific processes, environmental conditions, historical traditions, and poetic interpretations. The stars' vibrant dance reminds us vividly of our dynamic planet, our atmosphere's subtle complexities, and our enduring fascination with the beauty and mystery of the universe. Next time you gaze skyward and see a star vividly shifting colours, perhaps from radiant blue to fiery red to soft green, pause and appreciate the profound depth behind this simple phenomenon. Remember that you are observing atmospheric dispersion in action, light separated into its cosmic rainbow by Earth's invisible atmospheric prisms. Each twinkling, colourful star tells an ancient yet ever new story, a story of distant starlight transformed moment by moment into a dazzling spectacle, forever enchanting human eyes, minds, and whole age. Long before modern meteorology and sophisticated forecasting techniques, human beings relied heavily on natural observations to predict weather. The sky served as one of our oldest and most reliable sources of weather guidance, filled with subtle clues and signals, among them the twinkling of stars. Though it may seem surprising today, star twinkling was once a practical and deeply respected indicator used by ancient sailors, farmers, nomadic tribes, and indigenous communities to forecast impending weather conditions. This ancient art of sky interpretation, reading the stars and their delicate flickering, reveals an intricate, profound connection between atmospheric conditions, astronomy, and the daily lives of countless generations. But how exactly can star twinkling predict weather? The answer lies in understanding the underlying atmospheric processes that cause stars to twinkle in the first place. Recall that twinkling, or atmospheric scintillation, occurs because starlight is refracted and disturbed as it passes through layers of air with different temperatures and densities. The greater and more turbulent these differences, the more vigorous and noticeable the star's twinkling becomes. Because weather changes, particularly storms, shifting wind patterns, or rapid temperature fluctuations, often increase atmospheric turbulence. Observing heightened or intensified star twinkling provides a subtle yet powerful clue that the weather may soon shift dramatically. Consider an ancient sailor navigating the open sea. Without modern tools or forecasts, sailors relied profoundly on their ability to read subtle signs from the sky, water, and air. Observing the stars was crucial. If a sailor noticed stars twinkling more intensely or vividly than usual, particularly stars low on the horizon, which react more sensitively to turbulence, they might suspect an approaching weather system. Increased twinkling indicated stronger atmospheric turbulence, often signalling changing wind patterns, shifting temperatures, or a developing storm. Such observations could be life-saving, allowing sailors to take precautions, shortening sails, securing the ship, or steering toward the sheltered waters. Similarly, farmers across diverse cultures closely watch the twinkling stars as part of their nightly routine. Farmers depended heavily on weather conditions for successful planting, harvesting, irrigation, and protecting crops from unexpected storms or frosts. A sudden increase in twinkling, particularly accompanied by rapid colour shifts, often indicated upcoming weather changes, such as approaching storms, temperature inversions, or sudden cold fronts. In response, farmers might adjust planting schedules, hasten harvests, protect livestock, or prepare irrigation systems accordingly, all guided by the subtle flicker of distant stars. Nomadic tribes, indigenous communities, and pastoralists around the world also integrated star twinkling into their sophisticated traditional ecological knowledge systems. Observing star twinkling complemented their knowledge of animal behavior, wind patterns, cloud shapes, and environmental cues. Intensified twinkling often warned them of impending shifts in weather, cold snaps, storms, or sudden warming periods, guiding decisions about migration routes, animal grazing, shelter, and resource management. The skillful reading of stars thus became deeply embedded within broader ecological and cultural practices, contributing to survival and resilience in diverse environmental contexts. Historically, documented evidence from cultures around the world emphasizes how star twinkling served practical forecasting purposes. In ancient Greek texts, Roman maritime manuals, Chinese astronomical records, Indian Vedic literature, and Native American oral traditions, heightened star twinkling consistently appears as an omen or indicator of changing weather. Greek and Roman navigators noted increased star scintillation as a precursor to rough seas or storms, advising mariners accordingly. Chinese astronomers meticulously recorded the intensity and patterns of star twinkling, correlating these observations with weather phenomena like rain, wind, and temperature changes. Vedic traditions from ancient India describe vividly twinkling stars as warnings of impending monsoons or storms. Native American cultures also incorporated star twinkling into seasonal calendars, associating intensified twinkling with shifting weather patterns vital for agriculture, hunting, and migration. Modern science validates these ancient practices. Increased atmospheric turbulence, signalled by intensified star twinkling, is indeed often associated with approaching storms, fronts, or significant temperature fluctuations. Rapid vertical movements of warm and cool air masses, characteristic of stormy or changing weather, enhance atmospheric turbulence, causing stars to twinkle more vividly. Additionally, rising humidity or moisture ahead of rain or snowstorms can increase atmospheric refraction and turbulence, amplifying twinkling noticeably. Interestingly, modern astronomers and atmospheric scientists still rely on the principles behind this ancient observational art, though they use sophisticated instruments rather than their eyes alone. Astronomers routinely measure atmospheric turbulence and star scintillation patterns with precision instruments called seeing monitors or scintillometers. These instruments precisely quantify how vigorously stars twinkle, providing detailed insights into atmospheric conditions. Such data help astronomers choose optimal observational times and also contribute to meteorological understanding by revealing subtle atmospheric changes preceding significant weather events. Meteorologists and climate scientists similarly recognize star scintillation as an informal, visual complement to formal forecasting tools. Though not regularly employed for official weather forecasting today, observing star twinkling can still serve as a useful informal indicator of atmospheric instability or impending weather changes, especially in remote or rural areas lacking modern forecasting infrastructure. Outdoor enthusiasts, campers, hikers, and those living in isolated locations continue to rely on star twinkling to gauge nightly atmospheric conditions informally, blending modern knowledge with ancient observational traditions. Culturally and poetically, the relationship between star twinkling and weather prediction enriches human imagination and symbolism. Ancient cultures interpreted heightened twinkling stars poetically as messages, omens, or communications from divine or cosmic realms warning humans of upcoming changes or dangers. In myths and folklore worldwide, vividly twinkling stars often symbolize prophetic insights, mystical awareness, or divine foresight, linking celestial phenomena with human destinies. Such interpretations add emotional, spiritual, and poetic depth to practical weather forecasting, illustrating the profound interconnectedness humans historically perceived between sky, earth, and daily life. Thus, the ability to forecast weather from star twinkling embodies a deep synthesis of practical knowledge, scientific principles, historical traditions, and cultural symbolism. It reminds us vividly that science, tradition, and poetry intertwine profoundly in human experience, each complementing and enriching our understanding of the natural world. Next time you observe stars twinkling more vividly or energetically than usual, consider pausing for a moment. Reflect on the ancient wisdom embedded within this simple observation. Imagine generations of sailors, farmers, nomads, and sky watchers looking upwards, interpreting subtle changes in twinkling to guide their decisions, protect their communities, and navigate uncertainty. In this moment, star twinkling becomes more than an astronomical curiosity. It becomes a timeless connection to human history, practical wisdom, and the living rhythm of Earth's weather, reminding us of our profound, enduring relationship with the natural world around and above us. While the gentle twinkling of stars can captivate casual observers, enchanting them with shimmering beauty and colour, this atmospheric effect present significant challenges for professional astronomers. The same phenomenon that creates a romantic, dreamy night sky for casual stargazers can significantly hinder scientific observation, blurring images, reducing precision, and complicating astronomers' ability to conduct detailed studies of celestial objects. Astronomers refer to this challenge as atmospheric seeing, a term describing how clearly and sharply they can observe celestial bodies through Earth's turbulent atmosphere. Poor seeing conditions occur when atmospheric turbulence is intense, causing stars to twinkle vigorously and images to blur. Even slight atmospheric disturbances, invisible to the naked eye, can drastically reduce the resolution and clarity of telescopic observations, significantly impacting research. Consider a professional astronomer aiming to study a distant galaxy, a faint nebula, or the surface features of a planet. Precise measurements require stable, high-resolution images, revealing subtle details and allowing accurate observations. But atmospheric turbulence, manifested as star twinkling, constantly shifts the position, brightness, and clarity of celestial objects. Through a telescope, vigorous twinkling turns sharp images into blurry, indistinct smudges, erasing subtle features, details, and essential data points. Such instability significantly limits astronomers' ability to measure precisely, analyze phenomena accurately, or capture clear images necessary for groundbreaking discoveries. To understand the scale of this challenge, imagine reading a small print book underwater through moving, turbulent water. Each small ripple distorts the text, making reading difficult or impossible. Atmospheric turbulence creates the same effect for astronomers. Instead of crisp, stable images, astronomers see blurred, shifting, distorted versions of celestial bodies, compromising their ability to analyze light spectra, measure stellar positions accurately, or observe transient phenomena like distant supernova or variable stars. Historically, astronomers struggled profoundly with this challenge. Before modern technology, astronomers painstakingly observed celestial objects multiple times across different nights, averaging observations to reduce turbulence effects. Such efforts required patience, precision, and meticulous attention, yet still yielded limited accuracy. Many early astronomical breakthroughs, from mapping lunar surface features to studying planetary details, occurred under frustratingly unstable atmospheric conditions, significantly limiting the pace and scope of discovery. Today, astronomers employ advanced technologies and methods specifically designed to overcome atmospheric twinkling and turbulence. One groundbreaking solution is adaptive optics, a revolutionary technique dramatically improving observational clarity despite atmospheric distortions. Adaptive optics systems employ specialized sensors, rapidly measuring atmospheric turbulence in real time by monitoring reference stars or artificial laser guide stars. These systems relay detailed information about turbulence patterns to deformable mirrors inside telescopes. In response, these mirrors continuously adjust their shape, counteracting atmospheric distortions in real time. This advanced correction technology effectively neutralizes turbulence effects, transforming blurry, twinkling celestial images into sharp, stable, crystal-clear pictures, enabling astronomers to observe and analyze celestial phenomena with unprecedented clarity and accuracy. Another powerful approach to mitigating twinkling is positioning observatories in strategic locations. Astronomers establish observatories atop high mountains, isolated deserts, or remote islands, locations specifically chosen to minimize atmospheric turbulence. High-altitude observatories, such as Mauna Kea in Hawaii, the Atacama Desert in Chile, or the Canary Islands, sit above substantial portions of turbulent atmosphere, significantly reducing twinkling and improving seeing conditions. Such locations offer consistently clearer, steadier images, maximizing observational quality and precision. Perhaps the ultimate solution to atmospheric twinkling is space-based observation. Space telescopes, like the renowned Hubble Space Telescope, the James Webb Space Telescope, and many specialized astronomical satellites, orbit Earth beyond the disruptive influence of our atmosphere. By completely eliminating atmospheric interference, these telescopes capture perfectly stable, ultra-high-resolution images, revolutionizing astronomy by allowing scientists to see deeper into space and capture faint phenomena with unmatched clarity. Space-based observation has unlocked countless groundbreaking discoveries, from imaging distant galaxies billions of years old to detecting planets orbiting distant stars, precisely by overcoming the limitations imposed by atmospheric twinkling. Despite these technological advances, twinkling remains a persistent, practical concern for astronomers, particularly those operating ground-based observatories. Astronomers meticulously monitor seeing conditions daily, carefully timing their observations for nights with minimal atmospheric turbulence. Extensive databases of historical seeing conditions guide observational scheduling, enabling astronomers to select optimal moments for conducting precise, detailed research. In this way, managing atmospheric turbulence remains a fundamental part of astronomical practice, an ongoing, subtle negotiation between scientific precision and Earth's dynamic atmosphere. Beyond its practical challenges, atmospheric twinkling holds deeper philosophical implications for astronomers. It reminds them continually of Earth's dynamic nature, the subtle complexities of the environment surrounding their telescopes, and the remarkable interplay between distant celestial phenomena and immediate earthly conditions. Observing twinkling, astronomers remain aware that their understanding of the universe is constantly mediated through a living, breathing, dynamic planet, an awareness that fosters humility, curiosity, and profound respect for nature's subtle influences. Despite its challenges, atmospheric twinkling contributes something profoundly valuable to astronomy: a sense of wonder, humility, and continuous striving toward improved observation. Each attempt to overcome turbulence brings deeper understanding of optics, atmospheric science, and technology, enriching astronomy's depth, complexity, and human significance. The delicate dance of atmospheric twinkling thus serves not only as a practical obstacle, but also as an ever-present reminder of astronomy's profound interconnectedness with Earth's atmosphere, weather, and environment, an enduring symbol of the balance between human inquiry and nature's subtle yet powerful influence. For those who gaze at the stars, whether casual observers or professional astronomers, observing through Earth's turbulent atmosphere remains both a practical challenge and a profound reminder of our planet's influence on how we see the cosmos. Every astronomical observation made from Earth necessarily involves viewing distant celestial bodies through the invisible yet ever-moving veil of our atmosphere. This experience defines how we perceive, understand, and appreciate the universe itself. Every star, galaxy, planet, or nebula observed from Earth comes to us filtered through atmospheric turbulence. A turbulent veil created by shifting air masses, changing temperatures, wind patterns, and moisture variations. Observing celestial objects through this turbulent atmosphere profoundly shapes our astronomical understanding, requiring astronomers to continually adapt methods, techniques, and observational strategies. Observing through the atmosphere has always guided astronomy's evolution. Early astronomers carefully chose observation locations, preferring stable climates, high altitudes, or desert environments where atmospheric turbulence minimized observational disruptions. Ancient cultures built observatories atop mountains or high plateaus, locations still preferred today precisely because they reduce atmospheric interference, allowing clearer, steadier views of the cosmos. Modern astronomers further refine observational strategies by incorporating sophisticated technologies designed to mitigate turbulence effects. Adaptive optics, atmospheric dispersion correctors, and advanced telescope designs all emerge specifically to address atmospheric challenges, highlighting astronomy's continual adaptation to Earth's turbulent atmosphere. Yet despite technological advances, observing through Earth's atmosphere retains profound emotional and philosophical significance. Observers know each image, each observation, contains within it a subtle signature of Earth's atmosphere. Every star flicker, every subtle shimmer, reminding observers of our planet's dynamic environment. Observing celestial phenomena from Earth thus constantly intertwines astronomy with atmospheric science, meteorology, climate study, and environmental awareness. Indeed, observing stars through atmospheric turbulence symbolizes astronomy's broader interconnectedness with Earth's environment. Each observation reminds astronomers and all sky watchers of Earth's atmosphere's fragility, dynamism, and influence, reinforcing appreciation for environmental stewardship, climate awareness, and ecological responsibility. In conclusion, the gentle twinkling of stars is far more than an optical curiosity. It embodies the profound, intimate relationship between Earth, atmosphere, observer, and cosmos. Each flicker, shimmer, or colourful flash offers a quiet, continuous reminder of atmospheric physics, weather dynamics, historical traditions, human curiosity, and cosmic wonder.